Hello, everyone. My name is Kayla, and these are my teammates, Justin, Anna, and Torin. Today, we're going to be telling you about RIPT, our rapidly inflating pneumatic tourniquet. A tourniquet is a medical device used to cut off distal blood flow in cases of life-threatening bleeding from a limb. RIPT is unique because we're taking a device used primarily by trained EMTs, and we're making the functionality simple, fast, and accessible for civilian use. Dr. Jose Pascual is our mentor for this project, and he, along with his colleague, Dr. Sharik Raza, have been critical in guiding our project from the medical perspective. They are both trauma surgeons at Penn Presbyterian Medical Center, and when we first came to them with this concept, they were extremely enthusiastic because they see the need for a device like RIPT in their careers day in and day out. Trauma is the leading cause of death in people under age 46 in the United States, and 1/3 of these deaths are related to blood loss. A trauma surgeon who cared for critically wounded victims at the Pittsburgh shooting at the Tree of Life Synagogue this past October estimated that tourniquets saved the lives of at least 3 victims that day. There's a current initiative started by the American College of Surgeons called Stop the Bleed in response to the growing number and severity of these active shooter events. One of the main goals of this initiative is to stock bleeding control kits in public venues such as schools and stadiums, anywhere that an AED would be located. In cases of emergency, when life-threatening bleeding control is necessary, oftentimes civilians are there before first responders arrive. And we believe that in order to ensure the public safety of all civilians, a device like RIPT should be readily available in all places that an AED is located. And now, Justin will tell you about some of RIPT's competitors.
So here you'll see the combat application tourniquet. It's a non-pneumatic tourniquet that operates using a windlass mechanism in which a thin strap is wound tightly around a rod. It's the primary tourniquet employed by the U.S. military and is beginning to be deployed in some police departments across the nation. It's compact enough to be stored on one's belt and can be quickly deployed, but it's difficult to self-apply, and once applied, is extremely painful. Furthermore, the narrow strap of the CAT is associated with increased risk of nerve damage and lasting loss of limb function. And here you'll see the emergency and military tourniquet. It's a pneumatic tourniquet that occludes blood flow in the limb via the inflation of an air bladder surrounding the limb. This tourniquet is almost exclusively employed by the U.S. military. And though it is safer than non-pneumatic tourniquets like the combat application tourniquet, it is prohibitively high cost at about $475. This, in combination with the documented shortcomings in the EMT's durability, namely that it's prone to puncture, leaking, and abrasion, have so far prevented this tourniquet from seeing widespread civilian use. And finally, the device must be manually inflated using a hand pump as opposed to being capable of rapid and automatic inflation. A study conducted in 2014 tested volunteers without prior military or medical training on their ability to apply the combat application tourniquet. The application mechanism of the CAT proved cumbersome, as only 1 in 5 civilians were able to apply the tourniquet correctly. And even with training, this number only increased to 2 in 5. But we at RIPT hope to make this number 5 in 5 by way of RIPT's simplified application process, in addition to its increased comfort of application, the inclusion of pictorial instructions on the device itself, as well as increased awareness and incorporation in bleeding control training. So we've identified a number of key specifications in order to realize our plans to build a better tourniquet. In the first place, our device must be reliably able to reach appropriate pressures to occlude blood flow in a vast majority of cases. And the number that we have identified as being an optimal internal pressure is 250 millimeters of mercury. This is informed by our discussions with trauma experts Jose Pascual and Sharik Raza as a standard pressure for occluding blood flow in a vast majority of cases. Next, RIPT will occlude blood flow in the limb using smaller pressures and smaller pressure gradients than non-pneumatic tourniquets like the CAT, which will significantly reduce the risk of nerve injury, and it accomplishes this via the use of a wide band and its pneumatic mechanism. Thirdly, unlike the EMT, RIPT will not leak or fail when exerting high pressures. Emergency physicians have distrusted the EMT because they found that it wears out quickly and fails when damaged. RIPT, in contrast, will incorporate a durable outer protective sheet made of ballistic nylon, as well as an internal bladder made of tough rubber. Next, it is crucial that the device be reliable and easy to use by civilians who, as I mentioned previously, frequently apply tourniquets incorrectly. The way that we will accomplish this is via a simplified application process using automatic inflation via the release of pressurized CO2. Next, we want the device to be able to accommodate a wide range of limb girths. And the way that we will accomplish this is by a locking clip that you see here. And so ideally, the device will be able to accommodate from the small limb of a child up to the larger limb of a well-built adult. And finally, we want this all to be cost-effective and reasonably priced compared to existing solutions, which, as I mentioned before, are prohibitively high cost at nearly $500. In contrast, we want to make RIPT available for a sale price of less than $100.
Now we'll discuss RIPT's novel inflation mechanism while Justin provides a brief demonstration. First, he pulls a strap tightly around the limb and pushes down on the clip until the pin's locked into place. He then twists an inflator, releasing CO2 into the bladder, while a pressure relief valve regulates the internal pressure, ensuring that it stays at 250 millimeters of mercury. Our current and final prototype has a 3D printed and a machined aluminum clasp. It has to adjust the length of the bladder around the limb. It has spring-loaded pins that lock it into place to prevent airflow from going to the unused portion of the bladder. It also has our inflation mechanism has lightweight plastic fittings, and the strap is made out of a prefabricated neoprene bladder wrapped in a ballistic nylon outer covering. And finally, there are clear, easy-to-read instructions printed directly on the device so that a civilian could easily use RIPT. To ensure the effectiveness of RIPT, we tested key parameters to make sure that it's portable, durable, and accurate. When packaged, RIPT can fit in an 87.5 cubic inch container, and it is lightweight at 18.8 ounces. We're confident in the device's durability because the outer covering can withstand up to 900 pounds of weight before breaking. Also, the internal bladder can withstand repeated pressures up to 5,000 millimeters of mercury, which is significantly higher than the pressure that we're putting on it, which is 250 millimeters of mercury. Finally, we wanted to test the accuracy of our pressure relief valve, and after 10 trials, we found that it reliably released air after reaching 250 millimeters of mercury. Finally, we wanted to make sure that RIPT was easy to use, so we tested the time of application. And as you can see, RIPT took significantly less time than both the EMT and CAT, its main competitors, at just under 20 seconds. This is due in part to its rapid inflation mechanism, as well as its simple 3-step process, which is printed directly on the device. Now Torin will discuss our results.
So in order to evaluate RIPT and compare it to existing devices in the field, we outfitted a model limb that we constructed from a model of an upper arm with an array of force-sensitive flexible resistors. Keep in mind the values of these pressures at these resistors is less accurate than the internal pressure, as we mentioned previously, which is the gold standard used by physicians who are trying to occlude blood flow. However, this gives us a rough idea of the distribution of pressure at different points along the devices. So first of all, as you'll notice here, RIPT is comparable to the CAT in terms of pressure distributed around the circumference of the limb. This is crucial because, as you can see, there's a wide range of RIPT in which you can achieve a significant amount of pressure. Additionally, RIPT far exceeds the capabilities of the CAT in terms of axial pressure gradient. As you can see here, the CAT has along its center line, it has very high pressure, which drops off abruptly at its edges since the band is so narrow. In contrast with RIPT's pneumatic mechanism and wider band, it has a much more gradual gradient of pressure, which accomplishes our goal of reducing the risk of nerve injury. Also, it should be noted that pneumatic tourniquets have been shown to occlude blood flow at lower pressures than non-pneumatic tourniquets. Testing our device would fall under the OHRP category 4, since it's non-invasive and doesn't cause more than minimal harm. This means that we could test our device with an expedited IRB review in the future on actual human patients. Additionally, as a Class 1 medical device, pneumatic tourniquets are not subject to pre-market FDA approval, which means that all we would need to do is list our device and register with the FDA, and then we'd be subject to some quality system regulations, labeling, and reporting as well. Finally, with some brief market analysis, we've identified a number of potential users in the Philadelphia region as well as in the country for our product. Notably, both Penn and Temple have Stop the Bleed initiatives where they train hundreds of residents of Philadelphia in how to use tourniquets. Also, there are hundreds of public venues in the city which have an incentive to stock bleeding control kits in the unlikely event of a mass casualty situation. In addition to that, emergency service providers such as the police department and Philadelphia Fire Department currently stock a lot of tourniquets. The Philadelphia Fire Department is a major regional EMS provider, and the police purchase thousands of tourniquets under recent directives. In addition, the U.S. military is an enormous purchaser of tourniquets.
In summary, RIPT is a low-cost, easy-to-use, highly durable pneumatic tourniquet that outperforms the current gold standards for bleeding control. And we believe that in the hands of an untrained or trained civilian, RIPT has the potential to save lives. Over the course of our senior year during this project, we've utilized invaluable resources at Penn, and we would like to extend our thanks to these specific people and all these places at Penn. So thank you. And with that, we'll take any questions.
So obviously, whenever you pressurize air, fire extinguisher expires cost. Do you guys have any idea what that time period is and how likely it is that you'll go to throw the pressurized air on and come out?
So the canisters can be stored without cracking them open, and there's no significant leakage when they're stored that way, and they can be cracked open whenever you would need to pressurize the tourniquet. Yeah.
You talk about cost. Did you have an idea about roughly what this would cost?
Yeah, so the cost of our raw materials for the current prototype that we have is $48.55, including the clip, the ballistic nylon, the prefabricated bladder, and all of that. And we believe that if we were to extend to mass production, we would be able to get the cost of raw materials down. And we have an estimated price of around $85 right now. Thank you.
I was wondering about those canisters, the safety of an untrained user, perhaps puncturing it and then allowing it to escape from their hands and things like that. Have you thought about, or even cross-threading? Sometimes people, maybe if their hands are shaky, is there any way to mitigate that?
Well, they are threaded on the edge. And
So does it get punctured once it's securely in place?
yes, yes. It's punctured internally to this like inflator head mechanism. So we've never had any problems with it like flying off or anything like that. It's very reliable.
Were you able to do any tests on people that had been previously putting it on?
Not really, honestly.
You mentioned the range of sizes that it could accommodate, and you showed an upper limit. It would also work on compressing femoral artery on the side.
So,
Ideally.
so ideally, we would be able to make one that would be able to accommodate an arm and a leg. This current prototype would be just for an arm, but because of the locking clip mechanism that we can extend to not inflate the bladder, eventually it would be able to do that. Thank you.
Yes.
So has this been actually tested where fluid might be in between the limb and the actual device itself? Like, say, for example, the bleeding situation where you'd have some non-viscous material that's between it and how that affects the actual pressure of blood?
Right, so we didn't incorporate any kind of like artificial vasculature in our model arm or anything like that, and moreover, we weren't applying this to like living subjects or anything and actually measuring their pulse to see if their blood flow had
So
been
I'll ask the
included.
question again. Do you think that having fluid between your device and the actual limb would change the way that this thing would operate?
No, I don't believe so. Yeah.
The snugness, when you first put it on, there's a certain amount of snugness you probably have to achieve.
Yeah.
Otherwise, it's not going to work.
Mhm.
What's the margin of error in terms of how accurate you have to be with the snugness?
So in comparison to like non-pneumatic ones like the CAT, our margin of error is much higher, lower. We don't need to have as much snugness as solutions like those, which if they're not, if there's any slack left in them, there's a very high chance that you're not going to occlude the limb. Whereas with ours, we've seen, you know, the small amount of slack still permits like full pressurization.
Thank you very much.
Thank you.